Hi everyone, my name is Minmin Hou, and I would like to present my advanced data science capstone project, classification of air pressure system failures in Scania trucks with machine learning and deep learning models. First of all, a few words on the use case. The air pressure system, APS, plays a critical role in the heavy Scania trucks. It generates pressurized air that is used in a lot of important functions such as braking and gear changing. Previously, the trucks in a truck fleet have been checked periodically to examine the air pressure system to see if there's any problems with the system. However, there are problems with this approach. First of all, for those trucks that have healthy APS, it is a waste of resources to do such checkups. However, on the other hand, sometimes we can miss a faulty system, and that can lead to a breakdown afterwards, which could cost significantly much more and can also have safety issues. So the solution to these problems are that we can develop machine learning and deep learning models to help classify the status of the air pressure system. So the idea is that we can collect data from the trucks and we can feed those data into the machine learning or deep learning model, which are deployed either on board on the truck or as a service in mechanical workshops. And those machine learning or deep learning models can make predictions based on the truck data and give us either a pass where we don't have to do unnecessary checkups for the healthy trucks, or if we get a warning sign, then actions need to be taken to prevent breakdowns. So in this way, the operational cost of the truck fleet can be significantly reduced. So in this project, I developed machine learning and deep learning models to do such classification in order to reduce the operational cost. And I used the data sets which are downloaded from Kaggle, which is open source. And the data sets consist of data collected from the heavy Scania trucks in everyday usage. There were two classes in the data, the positive class and the negative class. So the positive class data was collected from trucks with APS failures, whereas the negative class data are collected from trucks with no APS failures. And the data was divided into training set and test set. The training set contains 60,000 entries in total, and 98% of them being negative and 2% of them being positive. The test set contains 16,000 examples in total. And for each truck, there are 170 attributes measured and recorded. So let me first walk you through one of the models that I developed, and then I will go into more technical details after the demo. So in this demo, I would like to walk you through a logistic regression classifier that I trained and developed. So the first step is to load in the training and test data sets into Spark data frames. And I used the Spark ML vector assembler to assemble the features into vectors that can be consumed by the Spark ML logistic regression function. And I also transformed the class labels into 0 and 1. Then I instantiated a logistic regression model, and I built a pipeline to then fit the logistic regression using the training data. After the training is complete, I make predictions on the test data. And to improve the performance, I also did hyperparameter tuning. So there's one parameter for the logistic regression classifier. That is the decision threshold. So I swept through a range of the decision threshold to find the threshold that can give us the best performance. And here are the results. So you can see that when the decision threshold is at 0.01, the cost is minimized. That means we have the best performing logistic regression classifier with a decision threshold at 0.01. So this is a quick walkthrough of one of the models that I developed in the project. Now let me go back to the presentation and dive into more technical details. So first of all, about the architectural choices. So I used cloud-based computing and storage platforms for this project to leverage the cloud computing resources. And I also chose to use Apache Spark for scalable and distributed parallel data processing. The reason behind this choice is that the training and test data sets, they have tens of thousands of entries, and the file sizes are in tens of megabytes. Although it's still possible to handle these locally and in serialized fashion, we can get a lot of benefits of distributed and parallel compute by using Spark. And what's more importantly, by developing on Spark framework in future when we want to scale out to deliver a real-world application or service to our customers, it will be easier to do the scaling out with the Apache Spark framework. And I use Python to do the programming because it's an easy-to-use programming language. And I also used PySpark, Spark SQL, and Spark ML to interact with the Spark framework because these are Python APIs that are more user-friendly, and they provide functionalities to do parallel data manipulation and machine learning. And for deep learning models, I used TensorFlow and Keras. They are widely used frameworks for deep learning, and Keras have many user-friendly Python APIs to build deep learning models. So the first step in this project is data quality assessment. So I looked at the data. I looked at the basic statistics, including the missing values, minimum, maximum, and quantiles of each feature. And I find out that there are a lot of missing values in the data. So nearly all the features have missing values, ranging from 5% to more than 90%. So that means we need to do feature selection and also feature engineering later on to deal with the missing value problem. So to further explore the data, I plotted all the 170 features in box plots to visualize the distribution of the negative versus positive data by each feature. Some features have clear distinctions between the two classes. For example, the AA000 feature on the upper right. You can see that there are clear differences between the two classes. So they are good candidates for model building. For some other features, for example, the AT000, for example, on the lower right here, you can see that there's no meaningful differences between the two different classes. So they may not be very useful when we come to train a model. So at the end, I selected 42 out of 170 features based on the two criteria. So first of all, they must show clear visual distinction between the negative and positive classes. And secondly, they must have less than 5% missing values in the training set. So after selected the features, I implemented the feature engineering methods. There were two different methods that I implemented. The first one is binarization, which means I transformed the continuous numeric features into categorical bins. And then I impute the missing values with the most frequently occurring number, either 0 or 1, for each feature. And the second method is scaling each feature by its maximum value and impute the missing values with 0. So more details can be found in my Jupyter notebook for the feature engineering module. So please refer to that notebook for more details, and I'll have links at the end of the presentation for your reference. Then we need to define a metric to measure the model performance. So a cost function was defined to measure the model performance. So it's defined as the number of false positives multiplied by 10, and plus the number of false negatives multiplied by 500. So you can see that the false negative is penalized much more heavily than the false positives. This is because when we have a false negative, we missed a faulty APS, and that can cause breakdown further down the road, and it will cause much more than when we have a false positive. That means we predict a healthy system to be not healthy and have someone check it. So the cost is much more to miss a faulty APS system. So the cost is defined as this, and the goal for the machine learning and deep learning model is to minimize the cost. So let me first talk about the machine learning models that I developed. As I've shown in the demo, logistic regression classifiers have been trained, and one of the hyperparameter, which is the decision threshold, has been tuned to minimize the cost on the test set. And here, in this table, I'm comparing two different logistic regression classifiers. The first one is trained with data that has been processed by the first feature engineering method, which is the binarization. And the second one is a logistic regression classifier that has been trained with data processed with the second feature engineering method, which is scaling by the maximum value. You can see that the first one performs better and achieved lower cost than the second one. So going forward, feature engineering method 1 was used for the deep learning models. Now let me talk about the deep learning models. So I implemented 3 types of neural networks in this project: feed-forward neural network, autoencoder neural network, and the convolutional neural network. There are a lot of details in the definition of the different layers and how the model is constructed and the training details. So please refer to my Jupyter notebook, the deep learning module, for more details. Here, as a summary, you can see that the convolutional neural network performs best among the 3, achieved around 17,000 in cost. However, compared to the logistic regression classifier, the cost is still higher. So in conclusion, I have developed machine learning and deep learning models in this project to make predictions on the failure status of the air pressure system in Scania trucks, with the aim to reduce the operational cost of truck fleet. And a training set of 60,000 records was used to train the models, and a test set of 16,000 records were used to evaluate the performance of the models. And of all the models explored in this project, the logistic regression classifier paired with the feature engineering method 1, the binarization method, achieved the lowest cost. So I would recommend to implement logistic regression classifier for our customers. So in future, we can explore more things in order to improve the model performance. For example, we can explore different selections of features and different feature engineering methods. And we can explore other machine learning models, for example, support vector machine or random forest classifier. And for the neural networks, we can do a lot more hyperparameter tuning. For example, try out different number of neurons in the hidden layers or different activation functions. So here I have links for the different Jupyter notebooks that I wrote for this project. They are divided into 4 different modules, and you can refer to these notebooks for more details of this project. Thank you.